Energy and work, wherein we look at the concepts of work, kinetic energy, potential energy, and conservation of energy. First, let's look at the concept of work. Put simply, energy is the capacity to perform work. When you have energy, you can perform work, and when you perform work, you basically use up energy. You can look at work as the capacity of a force to move an object along a displacement x. For example, you have an object, you apply force F on the object, and the object undergoes displacement x as shown in the figure. The force is said to perform work W on the object. The work done by force F on the object is given by W is equal to integral of F dotted with dx. Now note that this dot is dot product. So please review the concept of dot product in your vector analysis. Force unit is Newton. X unit is in meters, unit of length. F dotted with dx therefore will give you unit of Newton meter, which is given its own unit, joule. So the unit of work, unit of energy is joule or Newton meter. Now dot product is scalar product. So that means work and hence energy is a scalar quantity. Now dot product may be positive, may give you a positive answer or a negative answer. That means work may also be positive or it may be negative. If the work done by a force is positive, that means the contribution of the force to the motion is positive. Basically, the force increases the motion of the object. But if the work done by a force is negative, that means the contribution of the force to the motion of the object is negative. The force lessens the motion of the object. One way to see this is in terms of acceleration. We can say, for the most part, though not always, but we can say for the most part, when the work done by force on an object is positive, basically the object will accelerate. And if the work done by the force is negative, the object will decelerate. Now again, this is for the most part, okay, but not always. So this is just in general terms. So work is equal to integral of f dotted with dx. So next, we look at the concept of power. Power is the rate at which work is performed. Basically, we're talking about how fast a force is able to perform work in a given amount of time. Power is the rate at which work is performed. P is equal to dW over dt. Differentiation of work with respect to time. If we take the average power, this equation becomes P average is equal to total work done divided by total time or total elapsed time. So work divided by time, basically that's power. That's joules per second. That's given its own unit, watt. So 1 watt is equal to 1 joules per second. Another unit for power that you will commonly see, particularly when talking about machines, is horsepower or HP. 1 horsepower is equivalent to 746 watts. Now, if we talk about constant force, work is equal to integral of F dotted with dx. If the force is constant, the work equation becomes equal to simply F dotted with x. If we then use this equation to get the average power, work is divided by time. Work is F dotted with dx, so F dotted with dx divided by time will give you force dotted with average velocity. So average power, we have two equations if the force is constant. For constant force, average power is total work done divided by total time is equal to force dotted with average velocity. There are different types of energy. For now, for this point of our course, we will look at energy that is associated with motion. Aside from work, we have two mechanical energy to look at. First, we have kinetic energy. By definition, kinetic energy is basically energy associated with speed. As long as the object has speed, the object is said to possess kinetic energy. And kinetic energy is given by the following equation. Ke, kinetic energy, is equal to 1 half mv squared. Again, for the most part, m is considered to be constant, the mass of the object. Kinetic energy is equal to 1 half mv squared. And when force performs work on the object, one possible effect is the kinetic energy will change. So work is equal to delta Ke is equal to final kinetic energy minus initial kinetic energy. This is referred to as the work kinetic energy equation. Next, we move on to potential energy. Potential energy is brought about by conservative forces. A conservative force, when a conservative force performs work, the work done does not depend on the path taken by the object from initial position to final position. What's important is simply the initial position and the final position. The path taken from initial to final positions does not matter when it comes to the work done by a conservative force. The conservative force, when it performs work, the work done gets stored in the form of potential energy. By definition, potential energy is energy associated with position. One conservative force that we know of is the force of gravity. Hence, we have gravitational potential energy. Potential energy due to the force of gravity. Gravitational potential energy is given by the following equation. GPE, gravitational potential energy, is equal to mgh. When work is done, the potential energy may change. Work is equal to negative delta GPE. Is equal to final GPE minus initial GPE. Now, energy is a conserved quantity. That is to say, it is subject to the principle of conservation. For an isolated system, the principle of conservation of energy holds the following. First, energy is neither created nor destroyed, and may be converted from one form to another. Energy is neither created nor destroyed, so energy does not simply appear out of nowhere. It must have come from somewhere, and energy will not simply disappear, it must go somewhere. If an object suddenly gains energy, that means that energy must have come from somewhere. If the object loses energy, that energy will not simply disappear, it will go somewhere. For example, some other object might gain that energy that was lost by the first object. Energy may be converted from one form to another. Kinetic energy may be converted into potential energy. Work is converted into kinetic energy, and so on. Next, the total energy of the system is constant. That is to say, initial energy of the system is equal to the final energy of the system. For now, the energy of a system is comprised of kinetic energy and potential energy. So, energy of a system is just equal to kinetic energy of the system plus gravitational potential energy of the system. So, when we're talking about initial energy is equal to final energy, we get initial kinetic energy plus initial gravitational potential energy is equal to final kinetic energy plus final gravitational potential energy. This is our equation for conservation of energy. In particular, conservation of mechanical energy. If there is the presence of external force or forces whose work will either increase or decrease the energy of the system, we need to take into account the work done by these external forces in our energy analysis. We can adjust our energy equation into the following. Initial kinetic energy plus initial gravitational potential energy plus work done by the external force. So that's integral of external force dotted with dx is equal to final kinetic energy plus final gravitational potential energy. This is our adjusted equation for conservation of energy. If there's no external force, then the work done by the external force will be zero, and we go back to the first equation for conservation of energy. And that's it for now. In the next video, we'll continue our discussion on energy and work. In the next video, we will look at examples of energy analysis. So thank you for watching.